So thank you, Paolo, for your presentation. So I'm stop sharing because now I leave the stage to Giuseppe, who is online, and will please share your screen.
Yeah, thank you, Davide. And hello, everybody. I'm Giuseppe Sorrentino, and today I will accompany you beyond the limits of FPGAs, proposing a Versal-based framework for bilinear interpolation. But before describing the project, let me introduce myself. I am a PhD student in information technology. I'm a first-year PhD student at Politecnico di Milano, and my main research interests are reconfigurable architectures, federated learning, and image analysis. And regarding all these interests, today I will present a project that starts from the image transformation and extends it to the interpolation. Considering image transformation, it consists of moving a pixel from one position to another. This movement has some approximation, which lead to some errors. And the idea of the interpolation is to mitigate this error, so obtain as output a smoother image. This has a lot of different applications, for example, in mobile and robotics for digital zooming, or also in the healthcare domain for image registration. And given its importance, state-of-the-art provides a plethora of different algorithms to perform this interpolation. But among them, one of the most employed is bilinear interpolation, which represents the best trade-off between accuracy and performance. It consists on computing the output of a single pixel by combining the value of 4 different transformed pixels. And also considering the formula, essentially it is a weighted sum, it has some critical challenges. Indeed, we have to perform 4 transformations, so we have to perform 4 times memory accesses than simple image transformation. We have to perform intensive floating point computations to compute the weight and then lead to approximations and so to errors. And also, since the interpolation must be overlapped to the transformation, we have to parallelize it as much as possible. And it has a very complex parallelization due to random access pattern and data dependencies. Given these challenges, state-of-the-art presents some solutions, some software-based solutions, like SimpleITK, MATLAB, Cornea, or OpenCV. All of them achieve very high accuracy, but at the cost of performance or energy efficiency. To target very high performance, some of these state-of-the-art libraries also presents a GPU-based solution that achieves very high performance and still and high accuracy at the cost of energy efficiency. Indeed, GPUs are too power hungry, and so they cannot be employed in power-constrained scenario. On the opposite side, we also find FPGA-based solutions, which are very performant and also very high energy efficient, but they do not scale. Indeed, these solutions can handle only very small images, and considering 3D images, only small volumes can be analyzed. Given these limitations, today I will merge the benefits of AI engine and FPGAs to exploit the Versal system and creating an heterogeneous solution, achieving higher performance as a GPUs and also high energy efficiency as a common FPGA. Considering Versal systems, no state-of-the-art solution exists for the image interpolation. However, for the transformation, we have the previous talk. And if you have not attended it online, you can find it online on the Next Lab YouTube channel. We can use the image transformation presented by Paolo as an initial step for our interpolation. Considering the formula, indeed, we have to perform four times the image transformation, so we can replicate the presented design to parallelly perform these transformations. Then, given the formula itself, we have to compute the weights, and these are all floating point computations. For this reason, we rely on AI engines to perform this computation. Indeed, thanks to the AI engine API, we can compute up to 32 pixels per iteration. We can enhance performance, and we are less affected by the approximation of floating point computations. Furthermore, we tailor the procedure to perform this computation parallelly to the transformation step. According to the formula, we have to compute then the top and bottom factors, which are 2 independent factors. But as I said, we have to perform the interpolation in a streaming fashion, so within transformation. To do so, I devised two different coefficient interleaving and pixel interleaving mechanisms based on AI engine and PL respectively to give to coefficient and pixel a specific order. Let's zoom in the coefficient interleaving. We have 4 different AI engines computing 4 different coefficients. Thanks to the API, we can compute up to 32 coefficients per iteration. Then we can give this coefficient to other 2 AI engines that exploit the intrinsics, very highly optimized functions of AI engine to perform the interleaving. The first interleaving step allows to alternate coefficient. Then these alternated coefficients are given as input to another AI engine that performs another interleaving step to organize pixels in a very specific order. Indeed, in this stream, every 4 coefficients correspond to the coefficient required to evaluate a single pixel. Obviously, this order is effective if also pixel fulfills it, consider it. So also on pixel interleaving, we have to organize the pixels. Indeed, we take 4 volumes transform, so the 4 transformation, we give this volume to 2 different processing elements, and then this on PL, and this PL kernel performs the interleaving. This interleaving allows to enhance performance since we are exploiting also the transformation, the Giuseppe for 3D image registration, and so we are inheriting its assumption. Indeed, we translate on X and Y, and we rotate around Z, targeting a very domain-specific transformation for 3D image registration. In this case, the coefficient computed for a single pixel can be applied to all pixels depthwise, enhancing performance. These streams from coefficient and pixel are then given as input to 2 different AI engine components that can exploit the AI engine API to compute top and bottom factors. Thanks to this, we overlap the interpolation step to the transformation step, strongly reducing the execution times. And now, once all the components have been computed, we can finally compute the intensity of each pixel, of each output pixel, by a weighted sum. The computation is performed on AI engine, and then the result is returned to a PL component that saves it on memory. Indeed, the AI engine itself cannot access memory directly, so we have to use PL for this task. Well, this design is effective, but it's not efficient. Indeed, we have a bottleneck. We are still compute bound, and so we had to analyze each kernel of this design, and we highlighted as the bottleneck last part of this computation. So we duplicated this design, obtaining a 2 times speed up, so improving performance. To analyze the design, I used as a dataset a volume of 246 slices with a resolution of 512 times 512. So higher resolution than state-of-the-art solution based on FPGAs. At the device, I target a Versal VCK 5000, and I compare myself against Cornea, accelerated on high-end GPUs, as the A5000 and the A100, and also MATLAB, accelerated on RTX 4050 Mobile. To evaluate this performance, I use as key performance indicators the execution time in terms of seconds, the energy efficiency employing state-of-the-art metric, and accuracy in terms of mean square error. For the first analysis, considering the execution time, here the lower is the better, we achieve top improvement against Cornea, accelerated on A100 of 2.77 times, and we are comparable to MATLAB, which is a very highly optimized cluster solution accelerated on GPU. But considering the energy efficiency, and here the higher is the better, we achieve top improvement of 9.2 times against Cornea, accelerated on A100, and we are also more efficient than MATLAB with an improvement of 1.4 times. Then we also evaluated the accuracy of the framework of the solution in terms of mean square error, comparing the presented solution against Cornea and MATLAB. And the solution achieves a lower mean square error against Cornea and MATLAB than the mean square error between them. So we improve the accuracy of our framework, and we prove that we can apply it for real application as MATLAB or Cornea. This concludes essentially the presentation. The design methodology allows to create a bilinear interpolation algorithm that solves some specific research challenges. Indeed, we balance the workload between programmable logic and AI engine. We parallelize the transformation and interpolation, solving the issues related to data access pattern and data dependencies. And so we achieve high performance, high accuracy, and also high energy efficiency, the state-of-the-art solution. However, the work is not finished. Indeed, we can parallelize it even more, pushing the limits of versatile system capabilities. We can also relax the domain-specific assumption, and I'd like to relax them to create a more general application. And finally, since we had to consider 4 times the memory accesses of transformation, but we are transforming 4 times the same volume, I also would like to devise a caching mechanism to improve data locality. On this path, if you have some similar scenarios that can be parallelized thanks to the presented strategy, or other versatile devices that I can use to test my design, please drop me an email and I will be more than happy to work with you. Thank you for your attention.
Thank you, Giuseppe, for your presentation. So I have a question for you. You are talking about limits in of the proposed solution so far. So why you're talking about that? And do you have any plan to deal with them, or what else?
Okay, thank you for the question. Well, to improve the bottleneck, to solve the bottleneck, we duplicated the last part of the design. Now we are facing some limitation for the AI engine since we are exploiting all the streaming output of the AI engine itself. So we have to create a data duplication step to allow to use more AI engine and more interpolator components, and so improving the parallelization in the last step of the computation. So essentially, we have to create a data parallelization level, a data duplication level to improve the parallelism.
Thank you, Giuseppe. So this is basically concluding session of domain-specific computing. Please stay tuned because in 20 minutes from now, we will have the last but not least session. So I leave the stage to Mark.